Right, so welcome to lecture number 8, ME210 Fluid Mechanics, and we'll continue with our Reynolds transport theorem as we discussed it yesterday. I've written the form of the Reynolds transport theorem that we had derived yesterday. So it helps us relate the rate of change of B for a system with rate of change of B for a control volume, and then you get these terms which denote the inflow and outflow terms. I mean the quantity B, whatever it is, entering or leaving the control volume. Okay, and we had written this quantity as an integral over a control surface like this. Okay, so beta in this case is defined as the rate of change of B with respect to mass. So it's in the corresponding intensive property with respect to the extensive property capital B. Right, and what we can also do is, so remember this B control volume is the amount of B inside a control volume. So we can also write this B inside the control volume as an integral over the control volume. Then we can write beta times rho d omega. So rho times d omega is nothing but the infinitesimal mass. All right. So these are just different ways to write this Reynolds transport theorem. So that's one way where we can write the Reynolds transport theorem. In this case, what we've done is we have integrated over the area or the volume. So that helps us deal with situations where our density or beta, for example, is changing with different, it's non-homogeneous. So it's different at different points in space. So that ways we can calculate B in the control volume as an integral over the varying value of rho times beta over the different infinitesimal volumes in the overall control volume. That's that's the most general way to write it. I mean, if you have a situation where B is homogeneous, then you can simply use this form. Any questions? So let's now deal with some special cases. So once is when your control volume does not change shape. So remember, we discussed in the beginning that these control volumes can expand, they can contract. That is allowed, but there are situations where the control volume will not change any shape, its shape. So in those situations, we can, this term that we have here, you can absorb the time derivative inside the control volume, because these infinitesimal volumes that you have, these d omegas over which you are summing, they are also fixed because the volume is not expanding. So d omegas will also have the same size. So they will not change with time. So all you get is partial by partial t times rho beta times d omega. Now, if your control volume was expanding, for example, it was changing shape, then you could not do this, because partial by partial t of d omega in that case will be there. I mean, you have some contribution of the change in infinitesimal volume size as well. Is that clear? Now, another special case is when your control volume is moving. A classic example for this is a rocket problem. You have a rocket which is moving up with a velocity called v rocket, and it is releasing gases to get that thrust. So in this case, if I have to choose a control volume to solve this problem, the most apt control volume would be a volume which is moving with the rocket. Right? Because in fluid mechanics, you would want to figure out what is happening. What sort of forces are acting on the rocket, for example. So you would want to fix your frame with the rocket, like we did with car. So if a car is moving, we fix our control volume with the car and let the other fluid flow past it. So that's what we do in this rocket problem as well. And if you recall the Reynolds transport theorem, which has dB by dt for system and control volume like this, and then you have the control surface term, which is the b dot in and b dot out, which was rho beta v dot n times dA. So in this case, this v dot n came from the flow rate, right? So this was, remember in the beginning we talked about an area through which some flow is happening like this. So this v dot n that we have here is because of some flow entering or leaving the control volume. Now in this case, since your control volume is moving, which has, let's call this Vs, okay, the velocity of the system, or well, let's call this, because Vr you want to use for relative velocity. So let's call this VCV. That's much better. So this is the velocity of the control volume. So this v dot n term will have to be modified, because this v could be confused with the ground frame velocity. The velocity with respect to the ground frame. So this v called v relative. So this v will be the velocity of the gases with respect to the control volume frame. So if for some hypothetical reason the gases were moving with the control volume, okay, so that means that there is no inflow or outflow, because if a particle or a gas or a fluid molecule moves with the control volume, it will never leave or enter the control volume. So that way, this v dot n term has to be 0. So this Vr is the relative velocity of the fluid with respect to the control volume. So this is the fluid velocity in ground frame, in the absolute sense. Is that clear?
Yes, sir.
Okay, that's pretty much it. That's pretty much it for Reynolds transport theorem. There's nothing much here. So we are now in a position to start applying it. But before we apply it, let's look at this is the most general form, but we won't be applying this most general form all the time, because engineering situations would be much simpler. So let's call it, this is not a special case, this is one-dimensional approximation. So let's take an example here of a lawn sprinkler. Not a very nice circle, but that's how it is supposed to be. So you have a pipe which feeds in water in the center of the sprinkler, and then the water radially flows out and then leaves circumferentially like this. I'm sure you have seen this sprinkler. So this water that flows out results in a net angular momentum, and that water starts spreading in all directions. It's a very low cost and useful invention to irrigate farms. Okay, so in this case, what happens is if you're talking about the, uh, the flow analysis of this system, so what we do is we take a control volume, which let's use a different color, so which would look something like this. Let's say, let's take this as a control volume. That's our choice, so we can choose whatever control volume we want. So in this case, what you will see is that your integral over the control surface only has two terms, and both are, well, there is one inlet and two outlets. So I can write, so this is my inlet and these are my two outlets. So this whole term that we had, integral over the control surface, rho beta v dot n times dA, which basically came from b dot out minus b dot in. Now this, we don't need to evaluate any integral here because we know that there is one inlet and two outlets. So we can simply write this as summation over all the the two outlets minus summation over the inlets, but in this case you only have one inlet. Now moreover, what is this b dot outlet? So b dot is written as beta times the mass flow rate, m dot. That's how we defined the intensive property beta. So beta was dB by dm. Okay. So dB by okay, so we can write it this way. So what that means is we don't need to understand the velocity and area and so on, because we already know that what the mass flow rate out of that outlet is. When we solve the problem, this will become clear. So you don't need to write the integral form all the time. Sometimes life is much easier than evaluating integrals. Now there may be situations where the velocity is varying over the outlet. So in that case, you have to use the integral form. But in this case, we are assuming a uniform velocity. So this can be used if so if there's a uniform velocity over an inlet or outlet, then you can use this simple one-dimensional form. Any questions? So let's solve a problem. So this is a problem from the book that you can see. It's example 3.1. So I'll simply demonstrate that to you. Let's zoom into it a bit. So what we have here is we have a fixed control volume that's shown in this figure here, and it has three one-dimensional boundary sections. So you can see that there are two inlets, which are these ones, and there is, I'm using a mouse, please excuse me for the writing that we have, and then you have one outlet, that is number 3. And these are all one-dimensionals in the sense that you don't need to worry about the distribution of velocity over these areas. Simply inlet and outlet. Okay, the flow within the control volume is steady. So the word steady means that things do not change with time. So whenever you see the word steady, as we have discussed in the introductory lectures, then the partial derivative of that quantity with respect to time is 0. It's a steady state situation. Things do not change with time. The flow properties at each section are tabulated below. So you can see some properties, and you have to find the rate of change of energy of the system that occupies the control volume at that instant. So what we have to find is the rate of change of energy of the system that occupies the control volume at this instant. Okay, so let's go over the solution, then I'll explain things. So what you have is you have one outlet, that is number 3, and two inlets, 1 and 2. So what we do is we write the Reynolds transport theorem in this case with capital B as the energy of the system. Remember, we talked about that Reynolds transport theorem can be written for any extensive property. So capital B is also an extensive, capital E, that is energy, is also an extensive property. And the corresponding intensive property then becomes energy per unit mass, which is written using this small e symbol. Okay. So this dE by dt for the system is the dB by dt for the system in the Reynolds transport theorem. Then this term on the right hand side is your d by dt of capital E for the control volume. Right. Let's show you the equation again. So this dB by dt for the control volume is what your term, the first term on the right hand side of the equation is. Now this has been written by integrating over the control volume of rho times beta times the infinitesimal volume dV or d omega. Okay, and this term is going to be 0 because the system is steady. So steady means that there is no change of any quantity with time in the sense of in the control volume. So the partial derivative of all quantities including E and rho are both zeros. Okay, it's very important to understand this, that what is the meaning of steady. So steady is always in the control volume sense. Don't confuse that with the system sense. Now particle that is entering and leaving, that particle's energy could be changing for some reason. It's doing work or giving heat or doing something. But if you look at the control volume, and you look at, let's say, one point on the control volume, let's say this point here. So what you will see is that the density at that point or the energy per unit mass at that point, all quantities at that point in space will not change with time. So that's the idea of things being steady. If you were to put a probe there and measure something, some quantity, you would not see any change in that quantity being measured by that probe with time. Right, and then on the right hand side, the other 3 terms are simply the control surface integral terms. In this case, we are using the 1D approximation. So there are 2 inlets and 1 outlet. And in this case, I think the velocities are given. So these are velocities going out normally. So you can multiply the velocity by the area to get the volume flow rate, and you multiply that by the density to get the mass flow rate. So that will give you the three mass flow rates, M1 dot, M2 dot, and M3 dot. Is that clear? And then you just put values, and that will give you the rate of change of the energy of the system with time, and that comes out to be a negative value. Any questions on that? I'll stop sharing the problem screen. I've come back to my iPad screen for writing. We still have a couple of minutes for the quiz. So if there's any question, I am happy to answer that. I'll give you 2 to 3 minutes to set up open Moodle and so on. So what we found out for that example 3.1, the integral over control volume partial by partial t of beta times density, this term was 0, and that was 0 because we're talking about a steady state situation. And that resulted in dE system by dt being negative 0.24 megajoules per second or megawatts. Okay, so that was the net change in the energy of the system at that instant. So if whatever control volume we had, if at that time we have some molecules that are inside the control volume, so these molecules, if you're tracking the rate of change of energy of these molecules inside the control volume at a given time, that's the dE by dt of the system, and that's negative. And we'll worry about why it is negative, what can cause this to be negative or positive in the heat transfer course. But here we are more interested in finding out these values using our transport theorem that we have just understood. Now you can guess, I mean, it's negative because maybe it's doing some work. The fluid molecules are doing some work, and that resulted in its decrease in energy of those molecules. Or it could be that they are giving away some heat, and that heat loss is resulting in the decrease of those collection of molecules which constitute the system at that time. So we'll worry about the potential mechanisms of these loss of energy in the next year when you do the heat transfer course.